How do you learn Pythagoras' theorem? Let me show you how. Learning Pythagoras' theorem is actually quite a simple thing to do. The formula itself is quite short, and simply by practicing its use intensively over a short period of time, most students remember it quite well. If, however, you want to learn how to derive it or prove it, you've opened an interesting can of worms. Pardon the slang. I have here in my hand a book I was fortunate enough to obtain some years ago called the Pythagorean Proposition, and it was written 100 years ago by a gentleman called Elisha Scott Loomis. Now, in this book, he demonstrates, or at least lists, and summarises 367 different proofs. I've not added them up, but I've looked on the internet, and I'm assured that's the number in this book. He goes further than that and points out that there are in fact an infinite number of possible proofs of certain kinds. Now, many of them, as you can well imagine, are just variations on each other, but there are certain approaches. Now, we call it Pythagoras' theorem, but Pythagoras didn't invent it. In fact, Pythagoras was an amazing man who travelled widely. He spent many years in Egypt studying with the priests there, and we know that the Egyptians used Pythagoras' theorem before he was even there. He also spent a long time in Babylon at the time of the Jewish exile, and around the time that Zoroaster and others lived. Now, we know that the Babylonians were using his theorem centuries before he existed. Further to the east, we know that the Chinese used his theorem and had proofs of it, at least by about 1100 BC, some 600 years before Pythagoras. So in fact, he learned the theorem from elsewhere, but he was possibly the first to prove it geometrically. So there are geometric proofs, there are algebraic proofs. I'm going to show you one that the Chinese used about 1100 BC. It's probably one of the simplest algebraic proofs, and I think you'll like it. This is certainly a no-frills approach, but they start by talking about the triangle A, B, C. At least A, B and C are the lengths of the three sides of a right-angled triangle. If this is a right angle here, they knew that these other two angles added up to 90 degrees as well. I'm going to put a dot in one and a small cross in the other so we can keep track of them. The dot is between sides A and C, and the cross is between sides C and B. The Chinese made 4 copies of this. They made one copy and sat it here, so I'm going to try freehand to draw this. So this length would be A, because the triangle's been put up here. This was a right angle. This would have been B, and C would have been this side here. Now, this angle between C and B would now be up here, and this angle between A and C would be down here. Before we go any further, I want you to notice that if this angle with the dot and this angle with the cross add up to 90 degrees, that means that this angle with the dot and this angle with the cross add up to 90 degrees. But if this is a straight line and they make 90 degrees, then this has to be the other 90 degrees. In other words, it's a right angle. That is a most interesting and useful thing. Now, that's 2 triangles. They added a third one up here by picking this one up and placing it here. So let's go up another A and across at right angles, B, and this length is C. Notice again that if we pick this up, the angle between C and B is the one we're marking with a cross, and the angle between A and C, the one we're marking with a dot between A and C, is this one, And the same reasoning applies here. This is a straight line, so this must be a right angle. And they added a fourth triangle here. A and B and C. Again, between A and C, they've got the angle with the dot. So between A and C, here's the angle with the dot. Cross, dot, right angles. And between B and C, they had the angle with the cross. B and C, angle with the cross. Same pattern. So what they discovered is that by putting the same right angle triangle down 4 times, it not only creates a large square, but it has another square built inside it. What the Chinese did was they said this. The area of this large square must be the same as the area of the 4 small triangles plus this square in the middle. It's as simple as that. So let's work out how to express that. The area of a large square must equal 4 times the area of the little triangles plus the area of the square on the side. So I've just drawn that quite symbolically. So there's our area of a large square, 4 of the small triangles plus the other square. How do we find the area of a large square? Well, every side is A plus B. A plus B, A plus B, A plus B. So it's going to be A plus B squared, or A plus B times A plus B. What's the area of each triangle? Well, we need 4 of them. What's the area of each triangle? Well, the area of a triangle is half its length times breadth, or base times height. So it's half of A times B. And how do we find the area of the square in the middle? Well, it's the easiest part, because it is a square and each side is length C. So its area is going to be C times C, or C squared. Now, if we multiply this out, this sort of algebra is not often taught before Pythagoras' theorem, unfortunately. But we will multiply it out. We get A squared plus AB, and another AB is 2 ABs, plus B squared. Now here we have a number multiplying a fraction, and we can divide the 2 into the 4 goes twice. We have 2 lots of AB plus C squared, and we're in the fortunate position of finding that we have the same term on both sides of the equation. So we can simply remove the 2AB and we're left with A squared plus B squared equals C squared, which is the way we often learn Pythagoras' theorem. Now what it means, of course, if I draw a small diagram here, is that if I have a length A, B and C, it means that if I actually create a square on A, so this length is A and that length is A, so that is the square, and if I create a square on B, so this length is B as well, so that length is B, that area is B squared, and if I create a square on C, I'll shade this differently, horizontally. So this length is C and that length is C. Then if you cut these 2 squares up, they will exactly fit that one. This area is exactly the same as the area of these 2 added together. That's what A squared plus B squared equals C squared means. Interestingly, it applies to any shape, any regular shape built on the sides. So, for example, I know this is not very professional. We'll just try and remove a little bit of that. You could put all sorts of interesting shapes. For example, you could put a semicircle on each. and this semicircle plus that semicircle, the areas of those two semicircles add up to the area of that semicircle. You could put a pentagon or a hexagon on all three sides, and the two small areas would add up to the large one. So it's quite an extraordinary result, and it's used over and over again in our mathematics. What do I recommend? I recommend that you learn to draw this diagram, make this derivation. Again, that you do it once per day while you're concentrating on it. So, 1, set time aside. That means to focus, do the derivation, and then practice using it to answer all kinds of questions. So I'll put use, derive and use. You should do this often enough or intensively enough that you learn it well, and then you should use your diary to plan sometime in the future when you'll come back and revisit this to make sure that you haven't forgotten. I hope that's been of help to you. I look forward to seeing you in another video. Thank you for watching.